Kevin O'Leary is proposing a 9-gigawatt artificial intelligence data center in Utah, and the numbers are staggering. This single facility would consume double the entire state's current electricity usage. The waste heat generated would equal the thermal output of 23 atomic bombs every single day. This is not just a story about cooling servers. It is a story about how the physical limits of our power grid are forcing a complete overhaul of the business model for artificial intelligence infrastructure. By the end of this video, you will understand why the future of AI depends less on faster chips and more on who owns the power plant. To grasp the scale of this problem, we need to translate that heat metric into something concrete. A 9-gigawatt load is massive. For context, a typical large nuclear reactor produces about 1 gigawatt of electricity. This proposed facility would demand the output of 9 reactors running at full capacity, 24 hours a day, every day. But the electricity is only half the equation. The real challenge is the heat. Modern artificial intelligence processors generate immense thermal density. When you pack that much computing power into a single building, you create a thermal load that traditional air cooling simply cannot handle. Here is the thing that most people miss. The industry has been relying on air conditioning to solve this problem for years, but as we scale up to these hyperscale levels, the physics of air cooling breaks down. You cannot cool a 9-gigawatt facility with fans and vents alone. The energy required to run the cooling systems would consume a significant portion of the power generated just to keep the machines from melting. This forces a fundamental shift in the mechanical engineering bill of materials. We are moving from passive air cooling to liquid immersion or direct-to-chip cooling systems. This change is not just an upgrade, it is a complete redesign of how these facilities are built and operated. Quick resource note. I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. Now consider the impact on the local energy market. When you place a 9-gigawatt load in one specific region, you create what engineers call a load concentration risk. The local grid was designed to distribute power across a wide area, smoothing out peaks and valleys in demand. It was not designed to absorb a sudden, massive spike of power consumption in a single location. If the grid cannot handle the ramp-up, the result is not just a flickering light, it is a potential blackouts for the entire region. This means the local utility cannot simply plug the data center in and hope for the best. They must treat this facility as a baseload thermal plant rather than just another electrical load. This reality creates a paradox for developers. On one hand, the demand for artificial intelligence is exploding. On the other hand, the existing infrastructure cannot support the scale required to meet that demand without massive capital expenditure on transmission upgrades. The cost of upgrading the local grid to handle a 9-gigawatt facility is so high that it effectively turns the project into a de facto independent microgrid. The operator must secure its own fuel or renewable generation to avoid causing regional blackouts. This shifts the capital expenditure model from utility dependency to energy asset ownership. This brings us to the most critical insight. The sheer thermal density of these facilities forces a change in site selection strategy. For decades, data centers were built near fiber optic hubs to minimize latency. The goal was speed. But with the energy constraints we are facing, speed is no longer the primary driver. The new priority is energy arbitrage. Site selection is now driven by the availability of stranded or excess energy sources. In the case of Utah, the proposal relies on the potential for geothermal energy or other localized generation methods. The operator must vertically integrate power generation, perhaps through dedicated nuclear or geothermal plants, to ensure uptime. Because of this shift, waste heat recovery is no longer an afterthought. It is becoming a primary revenue stream. When you generate the thermal equivalent of 23 atomic bombs daily, that heat has immense economic value. Local municipalities are beginning to mandate district heating or industrial symbiosis partnerships to make these projects viable. The data center is effectively becoming a utility provider for the region, selling its waste heat to nearby industries or residential areas. This transforms the business case from a pure cost center into a diversified energy asset. This regulatory landscape is also shifting. The approval of such massive projects, despite public outcry, highlights a tension between property rights and grid capacity constraints. In some cases, the drive for artificial intelligence growth is overriding local grid limitations. This creates a business case for off-grid architectures where operators must take full responsibility for their power supply. The traditional model of relying on the utility company is becoming obsolete for hyperscale facilities. The operators must become energy companies themselves. The implications for investors and professionals are profound. The unspoken cost of the AI boom is the physical strain on utility infrastructure. If we cannot solve the energy and thermal challenges, the growth of artificial intelligence will stall. We are seeing a transition where the most valuable assets are not the algorithms or the chips, but the power generation and thermal management systems that keep them running. The companies that can master this integration will define the next decade of technology. Those that cannot will find their projects stranded by the very grid they rely on. The future of artificial intelligence is not just about code. It is about physics, thermodynamics, and energy economics. The shift from latency arbitrage to energy arbitrage is the most significant change in the industry's history. It changes where we build, how we build, and who pays the bill. As we move forward, the winners will be those who can turn waste heat into value and secure their own power supply in a world where the grid is reaching its limit. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.